I try to get this done in 5 to 7 minutes. So where you need to pause is where you need to pause on your own. Okay, so I'm just going to kind of keep talking through things, and if you need to pause, you should pause and take some notes. Okay, so, and that's the key, you should be taking notes. So we started with how we can deal with exponential equations and solve them using logarithms with this first formula. And like I said, I'm never going to make you memorize these formulas. You just have to be able to use them when you have them. Okay? So the first formula we already talked about is compound interest. And we talked about what all of these pieces of the compound interest were, and then we did questions regarding those. Okay? So today, we're not talking about compound interest anymore. We're going to talk about other types of exponential growth or exponential loss or decay. Okay? So something that we can think about is depreciation. And what we talked about in class was how something loses value, like a car, for example. A car, a boat, anything that you buy brand new and you take off the lot is going to be lose its value, okay? And so we have a formula for that as well, because it's not a linear loss, it's an exponential loss. All right? So what this means, n equals n sub o times 1 minus r, which is the rate, to the t, which is the time in years. And so what is the n and the n sub o? Well, I want you to be really comfortable with that, because as you can see, as you look down, you can see these in all three of these new formulas that we're talking about. Okay? Well, the n in this case for depreciation is the final value. The n sub o is the initial value, or the original value, which is why it's called n sub o, original value. Okay? And remember, so this is basically like with a car or something that we paid for that loses its value as it gets older. Okay? Then something very similar to the depreciation is the growth, but instead of subtracting the rate, we're going to add the rate. So how something grows, like a population. So you see how this is connected? It's the same n sub o, r, and t. It's the same thing as the depreciation. So these two are really interconnected. Okay? And then we have something that's called a decay for a half-life. All right? In chemistry, you may have learned that there are some elements, like mostly radioactive elements, that actually have something called a half-life. What a half-life is it means that if I have a certain amount of a material, it's going to take a certain number of years for it to decay, or to lose half of its element, right? So, for example, if I have, we'll just say that this piece of paper represents some element, okay, or compound, right? If this has a half-life of 10 years, then every 10 years it's going to decay. All right? And what you may have learned is the other half, if this is a radioactive element, this half actually decays and turns into lead. And so after 10 years, we have this half. So then after 20 years, again, it's going to be in half, because the half-life is 10 years. And then this breaks down again. So from the original, right, after 20 years, only a quarter of it is remaining, right? And then, again, another 10 years, and this breaks down again into half, and it goes away. And what's left over is that much. And that much happens to be an eighth of what the original thing was. And that's why this is exponential, because it's not a linear system. So what we're going to do is we're going to apply these three new formulas to some questions. So again, you should be pausing this, writing this down, and then pausing this next question and trying to solve it. So let's start with this one. Okay? It says, as construction increases, the population of a suburban town increases at a rate of 5.5%. prove that this population will double after 13 years. So this is basically the first question, and then this is the second question. So if it's going to double after 13 years, I don't really know what the population is, but I can give it a value because I'm just wondering when, like what time it'll take in order for this population to double. Okay? So the first thing we have to do, of course, is look back at our growth, our basic growth rate, our formula, n equals n sub o, 1 plus r to the t. So I'm going to write that here so we can follow this. N equals n sub o, 1 plus r to the t. Okay? So what does this mean? Prove that this population will double after 13 years. So we can just make up an initial number of people. And I'm going to use 1,000 just because it's easy, right? The number 1,000 is easy. So imagine if we started with 1,000 people. 1 plus, how do we write 5.5% in decimal form? We write it 0.055, because that's 5.5%. If I multiplied this by 100, it would be 5.5%. Okay? So prove that this population will double after 13 years. I know the t, so I'm going to put a 13 up there. So this is my question, like what, this number, in order to prove this, has to be 2,000 or greater. Right? So we have to see if this comes out to be 2,000. And the coolest thing about that is we simply put this into our trusty calculator, and we do the math, right? 1,000 with parentheses, 1 plus, or I don't have to do plus, 1.055 because I'm just adding that. And then I'm going to take that to the 13th power. And I'm going to hope, yeah, it's 2005.77. So this is approximately 2006. Well, what does that mean? It means after 13 years, and here's my statement I want you to be able to make. After 13 years, the population will approximately double. Okay. Now we can find what this is exactly, right? Because this is 6 people over the doubling, all right? But we're not going to do that. Well, yeah, let's do that. How long will it take for the town to double? Exactly. All right? So let's do that. Let's say, well, we only know an about, right? Because this goes above 2,000. So let's solve this for n. So now I know that this is 2,000 because I want to know exactly when it will double. And again, I'm just picking 1,000 because it's easy. And I'm going to do my math. And now this is to the t. So now is where we use our logs. If I divide everything through by 1,000, I can start writing this equation in log form. Okay, so let's be reminded how we do that. So log 2 equals log 1.055 to the t. We're using our rules. We take our exponent and bring it out here. And again, you should be pausing and trying this on your own first. So what does this come out to be? We do log 2 divided by log 1.055, and that gets 12.946. Does everyone see that? So 12.946. So let's say it's 12.95. So t equals 12.95. And I can figure out, well, how many months is 95/100ths of a year? 100x equals 95 times 12 is, right, we're cross multiplying, 1140. So x equals 11.40 months. So it's going to take 12 years, 11 months, and approximately half the year, so approximately 15 days, maybe a little less than that. And so that's the exact when it's going to double. So I'm going to show this whole thing again. I'm going to bring it up. I'm going to show this whole thing again, and I want you to really study this. This is our growth model. Now we must try our depreciation model. Okay? So a $40,000 car loses value the minute it is driven off the lot. If it loses 20% a year, how much is the car worth after 15 years? When will the car be worth $1,000? So of course, this is our first question, and this is our second question. So how much will it be worth after 5 years? So our depreciation is very similar to our growth, except we're going to subtract that rate. So I have N equals, it's a $40,000 car, that's my initial, that's my N sub O. 1 minus 0.20 because it's a 20%. Okay, so what else can I put in here? I can put 40,000. I can do the math, 0.80. And A is asking me, what will it be after 5 years? And I put that into my calculator. 40,000 times 0.8 to the 5th power. So it's going to be $13,107.20. So N equals $13,107.20. So after 5 years, this $40,000 car is only worth about $13,000 after 5 years. Okay, so that's like a huge loss, isn't it? So now let's do B. When will the car be worth $1,000? So that means we don't know what the T is, but we do know what our final value is going to be. So I put my 1,000 in my final value. I put my initial. I still do all of the same things, except I don't know my T, so I'm going to have to solve this using logarithms again. Divide by 40,000. Those 3's go away. Those 3 zeros go away. Can we all see this? Okay. So this equals 0.8t. And then I can put this into logarithms. Log 1 over 40 equals log 0.8 to the t. I use my laws by making my exponent a multiplication for my log. And just because I can, and because the fraction terminates, I can use 0.025 just to kind of make it easy for myself. 0.025. I divide everything through by log 0.8 log 0.8, and so t is going to equal whatever log 0.025 divided by log 0.8 is, and that means after 16, so t is 16.53 etc. years. So I can say after about 16 years, about 16 and a half years, the car is only worth $1,000. Okay? So that is the two that I want you to practice tonight. Okay? We're going to talk about half-lives tomorrow in math, but I want you to come to class with this formula so we can start working on those as well.